today's lecture. So today we will be going to discuss about the dimension, how to determine the dimension of the fractals. So first let us recall what we have done so far. So we have seen what is the definition of the fractals and why at all the fractals are important, and we discuss about the fractals are very common in nature, from cloud mountains to our kitchen, that is broccoli is also kind of structure which can be categorized as fractals. So we have seen that what is the fractal means. So fractals means infinite copies of self-similar objects, and it's may not be the case it always the exactly self-similar, but it could be the statistical sense, self-similar in statistical sense. So what do we mean by the statistically self-similar object? So it means that it is not exactly same, every objects are exactly not same, but they are differ only some fraction of things. So we are allowing that they are for occurring error with some probability, and that error is not one type of error, the error is statistically distributed through all structures. So that's it, that's kind of thing I am talking about now. So then we have seen, obviously we have seen how to categorize a countable set and incountable set, incountable infinite set. We have seen that the rational numbers are countably many, and whether the irrational numbers are uncountable, and we have seen that that's it. And then we have seen an example of a contour set, where we actually creating the contour set from removing that 1/3 part, and if I continuously do up to infinity, what we will get the contour set, and the contour set is a simplest kind of fractals, and these contour set holds some properties of the fractals. So that is basically the definition of the fractals. First of all, that the if I have a fractals, and if I zoom it in arbitrary small scales, we will find some kind of structure is there, some complicated looking structure is there. For example of contour set, if you go in the arbitrary small scale, and if you enlarge that scale, if you rescale that small arbitrary small region, you will find that a, a contour set which is reminiscent of the whole set, it is look exactly like the whole contour set, you will find in that arbitrary scale also, or rather than it is actually self-similar property what I am talking about. But what you will see, what do we mean by this complicated looking structure at arbitrary infinite small scale? I mean that you will find that at infinite arbitrary infinite small scales, the points are separates by different variable size of gaps. These variable size of gaps create a complicated looking structure. This is called the one of the property of the fractals, which means when in whatever small scale we go, we will find some kind of structure. It is quite contrary to our classical simpler objects like squares or planes. If I go at a arbitrary small scale, and the plane will be loose, means will be there will be no structure at all, it will be as as simple as it was before. So that is the thing. So it has some kind of structure, and it's to the contrary to the normal classical objects, which becomes more and more featureless when we zoom into the smaller and smaller region of that classical object. This is the first property, that is that it will be the fractal will contain complicated structure at arbitrary small scale. And second thing is, which is true for the fractals, for simplest fractals, and for if I say, that is called the self-similar structure. So we have seen that the fractals and this contour set is self-similar, and we find that whatever smaller arbitrary small size we go, you will find that self that smaller, or if I zoom that smaller arbitrary region, you will find that that smaller orbit, the contour part, or the subset means the contour set only that small part will be look like exactly similar to the whole contour set. So this means they are quite exactly self-similar, and it looks like that self-similar structure are the whole contour set made with self-similar structure at the arbitrary small scales. So it is not true for all fractals. Here the similarity is exact, but it could be also possible that similarity is in the sense of statistical sense. We will in this end of this class we will see an example of that. And third is this, that is called the C is self similar, and the third is that the dimension of these fractals are not always means it's in general in not integer, it is actually a fractional number, so that's why it is called fraction. So that's it. Now we have seen that the dimension is fractals. So now we want to actually measure this dimension. So to measure, now what in this class, so we have known the definition of fractals. Now what we want to do, we want to determine the dimension of a fractal. We want to know dimension of fractal. Okay, so first of all let us simplify, or let us so simplify the definition of dimension, then we will see whether or not the our classical definition of a dimension will work to determine dimension of fractals or not. So let's see that. So if I ask a question that what does this dimension means, suppose that we know that for familiar object, that we know that some rope is one dimensional object, some plane is two dimensional object, a cube or ice cream cube or ice cream cone is a three dimensional object. So what do we mean this dimension or dimensionality? And if anyone forces us to define this dimensionality in usual sense, what we will do, we will say that minimum number of coordinate minimum number of coordinate needed to specify needed to needed to specify needed to specify the location of each points location of each point in the set. So minimum number of coordinate needed to specify the location of each point in the set. So that's why we can define a coordinate, what define a this the minimum number is actually the minimum number is called the dimension, the dimension. So the minimum number of coordinate needed to specify the location of each point in the set is called the dimension. So in case of a rope, you know that whatever point you need, suppose you need this point, and if I say that this point is far away from this point O, this I want to need to determine this point D. So if I say you that this D point is a suppose a L arc length away from this point O, you can exactly find out where this point D is. So that is the original meaning of the dimension. Now for this and for two-dimensional object, we know that only two coordinate. So suppose here, suppose this is our two-dimensional object, so here some point is there, we know that we actually we can determine where this point is by only knowing what is the distance between from here to here and here to here. So only these and this, only two number is required to define the exact position of this point. So that's why it is two dimensional. Now if I ask the question that is this definition is sufficient for defining the dimension of the fractals, so is it sufficient? So let's check. So we will actually see that this definition is not sufficient for determining the dimensionality of a fractals. So that's why we will generalize this definition. I will modify this definition little bit so that we can define the dimensionality of a fractal. So let us first give you that the why we actually can't measure the dimension with using this definition. So let me give you an example, that is example of von Koch curve. von curve. So let me first make these things. So this is very interesting because by looking the von Koch graph is very interesting. I will show you our computer graphics first. Let us see what is the way to make a von Koch graph. So first of all, you will take a segment of line S0. Okay, suppose this is a length of some length L. Now what you will do, you will first take away this middle part, yeah, and the thing is take away means the similar as we have seen for the contour set. You actually take away this middle part. So this is S1, and what you will do, so this is, suppose this is total length is L, so this part will be L by 3 and this part will also be L by 3. Now what you will do, you will draw a equilateral angle with the same side L by 3 here. That's why this is S1. Now you will apply the same thing again. So let me copy it. So that's the thing. Now what you will do, now you repeat that exact process everywhere. So instead of these, you will now here you see that there is a line, and from line you will create this kind of structure. What you will do, the process is, you just you remove the middle part and replace it by the equilateral triangle. Now the same process I will repeat with every line segment. So let me remove this part. So let me draw here again. So first you will draw this part and this part, then you will do this like thing, then this part, remove middle third part, and you draw equilateral angle. Here also do same thing. So you will remove the middle third part and replace by equilateral triangle. So you see that the geometrical structure is very fascinating. It's I like the structure. Okay, S2. So you see this is S2. Now you imagine that if I infinitely repeat this process, so from, you see, from L, so from this straight line, from wherever you will find the straight line, any straight line, you will repeat the same process. So here also you start from here, here also you structure that this, and every straight line 1 2 3 4 5, every straight line you will do this kind of structure, and it will, you will repeat this structure to infinite times, and what you will get, that is called the von Koch curve. This is called von Koch curve. So if you say it's k, so k actually is infinity. So this is von Koch curve. Now you see that why it is fractal. So let's see. The first, that if I zoom out in any arbitrary scale, you will find the same kind of structure is everywhere. So that is first property. At arbitrary scale, there is a structure at arbitrary scale. Structure arbitrary scale. 2, that it is self-similar. And third, we will see the dimension. Dimension is fraction. So since these three property is satisfied with these by this von Koch curve, we will say this is a fractal. Now what is the problem? Now why we are defining is because we want to see a paradox that is related with von Koch curve if I use the dimension. So what is our definition of the dimension? So if I want to suppose know some point which is here, so what we will do, so we will see that what is the distance between, suppose, this point to this. Now one thing you can notice, that from that total length of S0, so first total length of S0 was L, but you see, first of all, this is S0. So suppose that you want to know where this point is, suppose end point is there. What is the distance between the end point? End point means I am saying that what is the distance between A to B. So this is the distance where this B point located with respect to A in the contour set, and in the contour set what is A0 is not contour set, K S infinity is the contour set. So let us process these things to the infinity, that's why we will get the distance, and if I know the distance, then we can say yes, indeed we can define. If I get the finite amount of distance between A and B, then we can say yes, indeed we can define the dimension the way we have discussed, that the distance between the minimum number of coordinates is required to describe. So first S0, Now length of S1, you will see the length of S1 will become 4 by 3L. Why? You see, so this is L by 3, this is L by 3, this is L by 3, this is L by 3. 4 L by 3 segment is required to reach A point to B point. So this is, now if I repeat, L is 2, you see, so this is L by 3, so 1/3, L by 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 such pieces is required, 16 L by required, so that means 4 by 3 square L. Now if I repeat, you will find that length of S infinity, or length at the von Koch curve, what is the length? This will be 4 by 3 to the power n into L, limit n tends to infinity. So you see, since 4 by 3 is greater than 1, so this is not finite, this is an infinite number. So 2, where does this point stays, means what is the distance between minimum distance between A and B, you will get infinity. Not only that, you see, this is only the single line case. Now here also, if you take for example for this point to A to B, so suppose this line is similar to this A0, only the difference is the first distance is L by 3. Now if I go up to infinity, you will find the similar logic, and you will find that the distance between, suppose let's see B, this is C, the distance between AC, if you length between S0, suppose S1 is L by 3, now you will find that in L S2 you will find that L by 3 into 4/3. Why? This L by 3, now you find that this is actually 1, 2, 3, 4 L by 9 pieces. So you see that 4 into L by 9. So that is right, actually that means L by 3 into 4 by 3. You will find that again you will go L length of S3, you will find that L by 3 into 4 by 3 square. Now if we go to infinity, so what is the length between A to C in the von Koch curve? You will find that L by 3, limit n tends to infinity, 4 by 3 by n. So this is also infinity. Now you find that every point, the distance between every point is become infinity at the von Koch curve. So in the limit of n tends to infinity, where this von Koch curve is, you find that every point is infinite far apart from each other. So the arc length between any 2 points is infinite. So that's why you can't describe where does this point by only one dimension. So what is happening here? So that is actually a paradoxical situation we have created here, because since by looking it's only this structure you have created this structure from the line segments, the dimension should be 1, but we create in such a way that it becomes fractals, and when it becomes fractals, the very smaller, this every points in this von Koch curve is infinite far apart, become infinite far apart from each other. So, and it is also obviously true that it is not actually two-dimensional object. So because if it was two-dimensional, it should contain some area, but you can see that it doesn't contain any area. So let me show you our computer graphics. Maybe I have some computer graphics. Okay, this is maybe You see, this is the von Koch curve. So let me, this should be there somewhere. Let me import it here. Where does it goes? Ah, you can see this is von Koch curve. This is very it's look beautifully, it's look beautiful structure. So this is the thing, and we have seen that any point, whatever point you take, so you will find that at the level of von Koch curve it goes infinitely far apart. So that's why we have to introduce some general definition of the dimension. So let's generalize the dimension for an object which is self-similar, and that dimension, definition of the dimension, is called the self-similarity dimension. Let's similarity dimension. So what does the similarity dimension means? So since the simplest fractals are self-similar, so that's why we are doing it. So what we will do, we will reduce the size of that object, and we will ask the question, if I reduce by a factor r, how many such object require to complete the whole. So let me give an example. Suppose I have a line. Now if I reduce the line by suppose factor r, so this is suppose L and this is L by r. Now if I ask the question, how many pieces of L by r, suppose this is L by r, this segment is L by r, so how many L by r is required to complete the whole? So you will find that if I put r these many segments, you will get the, so n of L by r is r. So you will, if we put r of these many smaller tinier size object, you will fill the whole object. Now the same thing, let's see for the square. Now if I reduce the every this every dimension, or it is called, so in every direction by 2, so suppose we are reducing the every direction by 2. So if I reducing the every direction by 2, I will get a square like this, which I filled with these red lines. So this is the square we will get when we reduce the size of the square in every direction by 2. Now how many these red pieces require to fill the whole square? So 1 2 3 4. So 4 required if I reduce. So if I reduce by 2, I required 4. Now if you find that in general, if you now again if you, so let me in general trend, so if I put it in r L by r, you will see that this will r square. You will find that r square amount of smaller boxes whose size, whose length of the every directions, or the length of the arm is L by r. So that L by r means r square number of total smaller size of arm length L by r is required to fulfill the whole square its number is r square. Now if I see the same thing for a cube, you will find that suppose there is a cube. So if I divide it into, means if I reduce its arm length in every direction by a factor 2, how many such tinier pieces I need to fill the whole bigger cube? So you will find that is 8. Now this is cube, now this is cube, this is square, so this is cube. So the drawing cube is very hard, so that I am skipping that part. Now this is, you will find that you will find 8. Actually for general cases you will find n by r is r cube. You see that the exponent of this, how many number of smaller thing we require, the exponent of that thing is not an this is not obvious, okay, is not accident, so it's not accident, so that's, it's actually telling us the dimensionality of the system. So here you find that how many it's required, r many is required. If I reduce by size r, if I reduce by size r, how many it's required, r square. And you see the exponent is 2 here, exponent is 1 here, it is one dimensional, it is two dimensional, and for three dimensional you find that it is actually 3. So that's where these exponents are actually telling about the dimension of the system. So that's why for the self-similar objects you can express what is the dimension of the system by this definition. D is, so let me first generalize this definition. So for a n dimensional objects, so if I reduce its one arm, means every arm, by a length r, how many required, how many smallest n dimensional objects I require to fill the whole is LR will be equal to r to the power n. So if I take logarithmic of every part, ln should be n log r. So that means the dimension will be log n by log r. So that is, this is the definition, this is the definition similarity dimension. This is the definition of similarity dimension. Why it is similarity dimension? Because we are creating similar objects in smaller size and check how many that smaller similar objects is required to fill the whole big object. Since we know the simplest fractals is a self-similar object, then we can also apply this definition, because we can take a tinier bit of self-similar object, a tinier bit of part of whole fractal, and if I see how many smaller size of these self-similar copies is required to complete the whole fractals, we know what is the dimension of that thing. So to see that, first we will see what is the dimension of the von Koch curve. So first, previously we find that it is not one dimension or dimension of von Koch. Previously what we seen, that it can be expressed in terms of one dimension. Let's see. So what is happening here? Okay, don't know. So let's see. So if I from here S0 to S1, you see the trend. If I reduce the size by 1/3, how many copies of straight line I require to fill the hole? 1, 2, 3, 4. If I reduce the size by L by 3, L by 3, 4, L by 3, 4 the simpler, these kind of 4 line segment only in tiny only reduce by a size 1 by 3, I need 4 copies of them, right? So this is repeatedly happening everywhere. So if I take suppose this part, so if I reduce by 1/3, how many copies it requires? 1, 2, 3, 4. 4 smaller line segment is required to fulfill to fill the whole L by 3 segment. So that means here if I reduce by factor 3, how many pieces I will have is 4. I means anyone need to 4 reduced by 3 factor line segment or line segment to fill the whole von Koch curve. So that means here the dimension should be D will be ln 4 by ln 3. So you see the dimension is not a integer but a fraction. So that's why it's fractal. Now let's check the dimensionality of the contour set. So what is the dimension? Means contour set C. So let us bring the contour set. Yeah, it is simple again. So you see here, so first this is the my whole, suppose this is not actually contour set but the property holds to infinity, which I am going to say. So this is, suppose this is the whole picture. Now if I reduce the size by 1/3, I need 2, means you see the 2 copies of this kind of straight line is created here. To fulfill this whole space I need 2 a tinier bit, and it is actually similar to everywhere. So if I reduce by 1/3, so if you reduce by, suppose this is the two whole contour set, so if you reduce by factor 1/3, so if you take only this many part, how many this kind of part required to fill the S5? So 1 and 2. So that's why here also R is, so if you reduce the contour set, any part of the contour set by 3, you need to have 2 copies of that reduced part to fill the whole space. That's why the dimension will be ln m phi ln r, right? So that is ln 2 by ln 3. Now if I go back to the definition of the fractals, you see I have shown you that the dimension of this contour set is ln 2 by ln 3, that is actually fractal 0.63. That's it. So that's how you measure the dimension of the self-similar objects. Now as we have said already that fractal is not the only, the simplest fractals are exactly self-similar, and here in the definition we have to have the self-similar objects, although we are reducing the size of that self-similar objects, but we need a tinier self-similar objects to fulfill the whole space. So that's why if my original fractal is not exactly self similar, we can't take a smaller part and ask the question how many of these copies required to fill the whole space, because at first that is not same as the whole picture. Suppose what I do I mean, so if you take any tinier part of this cube, it will still look like a cube, only a tinier version. Similarly, fractals means whatever smaller amount you take, that will be look exactly same. Fractals means I am saying about the contour set and the von Koch curve. How many smaller tinier part you will take from the von Koch curve, it will remain same as von Koch curve, only reduce in size. So but uh, every fractal is not like that. They are similar in statistical sense. So let me give an example, then you will find it. So first let me introduce the box dimension, then I will give you the example, and then it will be clear. Box dimension. So there are a lot of definition of the dimension. You will find it in the book of Falconer. Now in every dimension it is common that to measure the dimensionality, to measure the measure the dimensionality at scale epsilon, and in such a way that we ignores irregularities smaller than the epsilon, and epsilon obviously tends to 0, and then study and then study the behavior when epsilon tends to 0. So first we actually get rid of these all of the irregularities smaller than size epsilon. Then whenever we find epsilon, we now theoretically says if epsilon goes to 0, what was the dimensionality. So that's how the definition is. So box definition is, we use the size epsilon boxes, how many size epsilon boxes is required to cover the whole space S. Suppose, now let me give an example. So suppose this is a line. Okay, now it's weird. So suppose the size of the box is epsilon. Now how many such boxes I required to fill this whole length L? Suppose this is length L, A to B, the length of A to B is L, and the size of these boxes is epsilon. So how many these kind of boxes are required to fill the whole A to B? That should be proportional to L by epsilon. And if suppose in place of this I have some kind of area, now then you will make this kind of tinier box of size epsilon, means every arm epsilon, every square of length epsilon, how many such square is required to fill this whole space S? You'll find that will be in epsilon, that will be, if the area of this is a by epsilon square. Here also you find that the exponent, that it is exponent 1, it is exponent x is 2, that is not an accident, that is because of the dimensionality. This is the one dimensional object, this is the two dimensional object. So from this also we can define the object, the definition of the dimension. So dimension D will be limit epsilon tends to 0 ln epsilon by ln 1 by epsilon. So let us see whether or not this definition is matching with the similarity dimension or not. So first of, let us see it for Cantor set. So for the Cantor set, we know to cover these things, we know that 2 to the power n copies is required if I choose a smaller size of object of length 1 by 3 to the power n. So what I am saying, you will see here. Go here. So you see, so how many smaller objects required to fill this S0? So there are 2. So for S1 you find that 2 to the power 1 such object is required if I choose the box size of 1/3. So if I choose box size of 1/3, 2 such copies required to fill the whole space. Now in place of that, if I choose 1/3 square, that is 1/9, I require 1 2 3 4 2 to the power 2 size of 2 to the power 2 square number of such smaller pieces, tiny pieces, to fill the whole space. Now it's similarly, so that means, and this pattern is goes up to infinity. Now so that means, so 2 to the power n smaller copies required to fill the whole to fill the space if this epsilon, whatever epsilon I am taking here, if this epsilon is 1/3 n. So what is the definition of the dimension from here? What we will get? D will be, and when this here actually epsilon is 1/3 to the power n, and when this epsilon will goes to 0 when n tends to infinity, and in the n tends to infinity the actual at n tends to infinity the actual Cantor set is there. So limit n tends to infinity ln 2 to the power n by ln 1/3 to the power n. So ln not 1/3 actually, ln 1 by 1/3, so actually that will be 3 to the power n. So n will be cancelled, so ln 2 by ln 3. So that's it. So dimension is ln 2 by ln 3, which is exactly same as this similarity dimension. So that means it is actually, this is giving the same result as we have observed in the form of similarity dimension. Now let's go one step beyond. Now let's give an example which is not self-similar. So a fractal that is not self-similar is constructed as follows. A square region is divided into 9 equal pieces, 9 equal squares. SQU, and then remove one of them randomly. Then process, then repeat, then the process repeated on each of the remaining 8 small squares, and so on. So you finally do these things, and then what is the dimensionality? What is the dimension? What is the dimension? The box. Now you see it is not exactly self-similar. So let me create it. You will find it. Suppose this was my previous box. Now if I do in 3 part, it will automatically go to 9. Okay. Now let's remove some this part. So let me remove this part. So if I remove this part, so let's remove this part. Let's remove this part. Now let us now let's repeat the same thing with the tiny these every remaining 8 things. So now you randomly choose one thing and remove it. So from here you remove one part. From this segment, suppose you randomly remove this part. From here you suppose randomly remove this part. From here you remove again this part, this part, this part, this part maybe, and this part maybe. So if you randomly remove this part, so it actually become a fractals. So here you will find this thing. So you see that you actually not it is similar, but it's not exactly similar. It's actually similar in a statistical sense, because you are not taking away the same square every time. You actually is taking away random random square. So this piece and this piece are exactly equal, but you find somewhere this piece missing, somewhere that piece missing. So that is called the self similarity in the statistical level. Now if I ask what is the dimension of this, now uh, we can't use the self similar dimension, because you see that if I smaller it in one third pieces, it's not similar to this part, and this part is not similar. So I can't say. So this kind of 1 2 3 4 5 6 7 8 smaller pieces of square is required to fill the whole space, because we can't fill with this piece, because these pieces are not same as this. So that's why we use that thing, that at every time this is s0, at s0 we know that at s0 if I reduce the size one third, so suppose here epsilon is one third, we required 8 pieces, 8 smaller square to cover the whole space. Now if I here, if I reduce it by 1 by 3 square, you find that you will hear 8 1 2 3 4 5 6 7 8. So 8 into 8 such square, so 8 is square. So if you find this general 10, you will find that at Sn this f psi is one third to the power n, and m you find 8 to the power n. So at infinite, when it become the fractals, so when then dimension will be limit n tends to infinity, then it will become 0, epsilon tends to 0, because one third is less than 1. You will find that dimension will be ln 8 by ln 1 by one third, ln 1 by epsilon, so ln 3 to the power n. So n ln 8 3, so this is actually ln 8 by ln 3. So that's it. That's how you find the dimension of this not, which is not self similar object. However, with this box dimension also have some problem, and with those problems I will discuss in the next class, and we will see there is a another kind of dimension measurement which we actually use to measure the dimension of these fractals, which appears for the chaos, which is called the pointwise and correlation dimension, that we will see in this next class, Friday. And I think that will be probably the last class of this series, chaos and fractals. So that's it. Thank you.